Nimai Kormokar. My co-author is Imran Amin and Jontu Saha. We are from the Department of Electrical and Computer Systems Engineering, Monash University, Clayton, Victoria 3800. The title of the talk is Chipless RFID Sensor Using Smart Materials. I can be contacted via the following email address. The outlines are Introduction to RFID Sensor. Here I shall try to give you the importance. Why do we need RFID sensor in modern applications? Then state of the art in RFID sensors, followed by a smart material based RFID sensing device that we have developed in my laboratory. Then the configuration of chipless RFID sensors. Here we are also using single node multi-parameter sensing applications, and we develop this kind of device. Prototype development, and then we have also done the reader for chipless RFID sensor reading. And then finally I'll conclude my talk. The hypothesis or the goal of this work is we want to develop very low cost ubiquitous sensor that will be used for very low cost item tagging and sensing application, and that will have single node multi-parameter sensors. This book covers the main topic and my lecture is based on the topic. If you are interested to collect the book, you can go through the following citation. Evolution of tracking in ID technology. That is a very interesting chart developed by Dr. Imran Amin. You can see the first level started in 1930 by Avery. Still they are very active in RFID now. Then 1940 up to today, there are huge development in barcodes. If you read the article on optical barcode in Wikipedia, you will see the evolution has gone through tremendous technological challenges. And now we are seeing this 2D barcode and QR code with many data bits. And they are used in groceries, retails, patient tracking, whatever you can name it. Almost at the same time of barcode, RFID was invented in 1948, and then first uses was in 60s and 70s for very high cost application like nuclear security. Today, RFID are being used for keyless entry for our cars, security, e-passport, animal tracking. And if you look at the sensor, the first sensor developed by micro electromechanical system technology called smart dust in 1992. And now you can see a lot of active and passive RFID based sensors for different physical parameter sensing like temperature, humidity, strain, fluid level gauge, gas monitoring. However, RFID and the RFID sensor are very expensive, and that's why still barcode is quite prevalent and omnipresent. Until we can make the RFID and RFID sensor as a good competitor in terms of cost, there is no future. And that's why we're having this fully printable chipless RFID sensor. And that is our today's technology. You can see our first developed chipless RFID tag and sensor with two orthogonal antennas here shown in the circle with two disc loaded monopoles with multiple spiral resonators. One set of resonator, the single color, is used for ID generation, and the multicolor resonator they use for multi-parameter physical sensor design. What are the applications? The application of this chipless RFID sensor is huge. It could start from food safety, it can go up to the infrastructure, transportation, security, agriculture, a smart home, health, logistics, storage, emergency services. And the bottom three illustration shows some of the applications. Patient wristband or event management using wristband. The main impediment of chipped RFID is that you cannot have multiple RFID because they're quite expensive. But since chipless RFID is low cost. We can use multiple tags on the same wristband so that any arbitrary location of this tag can be read, and that is a big impediment for event management and patient tracking. Look at the smart home. We need so many varieties of sensors, and that only can be materialized by using low cost sensors that we are going to develop. Now we have developed different types of sensors so far. The potential of Monash microwave antenna RFID and sensor labs, chipless RFID sensor are as follows. What we want to offer to you, we develop fully printable, inexpensive. The cost will be couple of cents to sub-cent tag on plastic and polymer so that you can directly print on the packaging materials. We can also integrate RF sensing, that is the topic of today's discussion, in chipless tag. We have developed at least 20 different types of chipless tag, and now I want to add the sensing application with our tag. So this integration is very vital for current IoT, Internet of Things, and a smart home or a smart cities. We also develop in-house very low-cost reader for the tag detection as well as the sensing parameter reading. And the uniqueness of our team is that we aim to deliver a complete RFID system solution. And we have been publishing comprehensively in the field, not only tag, not only sensor, also for the reader as well as the middleware or the signal processing part of the reader. Our areas of innovation in chipless RFID sensor are in five folds. First of all, smart materials for identification and characterization of those smart material in microwave and millimeter frequency bands already has created a new field. So that is one innovation. A smart RF design, we normally do a lot of design, passive active design in microwave domain, but when you consider those physical parameters, then this design will be very complex, and that's why you need this smart RF design to consider all those physical parameter effect. Third one is integrated RF sensing. We develop multi-sensor framework and integration with the novel chipless RFID tagging concept. What we are doing here, we are keeping a set of frequencies for identification, for frequency signature, and another set of frequencies for the multi-parameter sensing. That way we created RFID tag and sensor on an integrated platform. Next is the CAD and CAM design and fabrication, micro frequency or millimeter frequency. It creates another field of research. As I mentioned to you, that a smart RF design doesn't mean only the passive or active design. It also needs to consider all the physical environments. Likewise, we need to have a comprehensive design tool like CST or HFSS or FECO or this kind of full wave EM solver, which can also deal with the physical parameter like temperature, humidity, etc. And we also have the CAM. We are using, for example, SATO printer in our lab, or we can have the 3D printer for additive manufacturing. We need this kind of innovation in microwave domain as well. Reader development. We need to develop very low-cost reader which is capable to read chipless RFID sensor data and quickly interpret the data into the right physical parameter. How can I do that? And these are the areas of innovation that we are creating, and I'm trying to explain this to you one by one. First of all, innovation in smart materials. What we have done, we have comprehensively investigated with our material engineering colleagues what smart materials provide, what stimuli in terms of physical sensing. For example, temperature, we are getting liquid crystal conducting polymer like PANI or P dot. For humidity, we have the huge band of materials here. For pH, we have very nice property of P dot. So here, the innovation in integrated multi-parameter sensing, the top figure is showing that the isometric view of the complete multi-parameter single node sensor layout here. So in the middle, the circuit shows the multi-slot patch resonator for data encoding. And you can see on the bottom photograph here also that shows the multi-slot for data encoding. That is U-shaped slot here. And these two metamaterial ELC coupled two metamaterials ELC1 and ELC2, they are used for the sensing data. For example, ELC1 is for relative humidity and ELC2 is for temperature. And you can see that we have three different slot resonators. They are giving fixed resonant signature and that contain the identification data. Whereas the ELC1 for relative humidity and ELC2 for temperature sensing, they are varying in close by frequency band within limit of band with the different changes of RH, relative humidity and temperature. Innovation 4, integrated RF sensor testing. This figure shows the photograph of the experimental setup. You can see how complex it is and how many pieces of equipment you need here. First one, we can see the Miller controller, and then there is a S key that creates the control environment, and this is the Agilent vector network analyzer. The experimental setup is shown in figure 2, and that is the photograph inside the S key. There is a data logger connected to the Bluetooth, and then the sensor is in between the two horn antennas. The horn antennas are connected with this vector network 2 ports. Look at the figure 3 where you can see with the controlled humidity there is a significant drift of this S21 parameter around 7 GHz, whereas the 3 identification data around 7.75, 8.25 and 9 GHz, there is no change. So this signifies the characterization of this sensor device for particular humidity sensor. Next innovation is the computer-aided design and computer-aided manufacturing. So we have done the design in CST and I mentioned that CST can consider other physical parameter along with this microwave characterization. Here the first left hand top photograph shows the shadow printer. It is a 600 dpi thermal transfer shadow printer available in my lab, and the right hand top picture shows the shadow printer printed chipless tag. Bottom side shows our vision that how we can materialize roll to roll inkjet printing technology, and we have been working with Xerox Palo Alto Research Center to develop this kind of printing head. One printing head will provide the sensing material and another printing head will provide the conducting material, for example the silver. That way we can create the roll to roll printing, on demand printing, that is very vital for this kind of low cost chipless RFID sensor design and development. Innovation 5, the reader development. Here the whole block diagram shows the operation of the whole system including chipless RFID sensor on the top as well as the reader three important blocks. First block is the RF section. It has two antennas, one transmitting, one receiving antennas, and then it has the transmitting circuit or transmitter circuit, the reception circuit, and also the digital section with digital to analog converter, analog to digital converter, microcontroller, graphical user interface. On the other hand, the power section that connects this 240 volts in Australian power system and then converts different voltage level from 5 volts to 15 volts to energize different sections of the RF and digital blocks. Finally, data acquisition system. Here I am showing the step-by-step data acquisition system. First, you acquire the data from the chipless RFID sensor. Then you have this ID data, which are fixed data, and then you have the sensing data, which is variable data in a particular band of frequencies. You have a lookup table or calibration chart that is embedded in your system, and then you can have your different kind of sensing data like relative humidity, temperature, pH, etc. That way we can quantify our measurable physical parameters using this fully printable low cost chipless RFID sensor. Innovation 5, reader hardware development. In the previous slide we have talked about the firmware development. Here I am talking about the hardware development. Since we are working in ultra wideband micro frequencies, since we have been working with ultra wideband micro frequencies, we have huge design challenge. Here I am showing some of the reader antenna development. On your top left side, figure A, that is a 4x4 planar array antenna with linearly polarized single port configuration. Figure B shows a single antenna with dual polarization. Figure C shows the 4x48 dual polarized antennas. So dual polarized antenna we are using to provide the polarization diversity to increase the data capacity to double. Bottom photograph shows our first developed conveyor belt based chipless RFID reader. Here the different sections like digital section on the top with keypads and also LCD display, the ultra wideband microwave transceiver section in the aluminum casing, and the antennas at the bottom. Then the side is the power supply. That's the first development. Recently we have developed the handheld reader in a commercialized packaging that can read the chipless RFID tag in between 4 to 8 GHz. Here, future application of chipless RFID, we have thoroughly investigated how we can implement our chipless RFID into commercial packaging. For particularly milk, you can see it has multiple layers, outer polythene layer, then paper board, and then inner polythene layer. And in the bottom side, we are showing the cross section of the implementation of the chipless RFID sensor. So the pH sensor material can be put on this yellow area, and that is the design layout for this sensor with ELC resonator for sensing and the U-shaped slot resonator for the identification data. Now, what is our unique contributions? Conclusion: the smart material have been identified and classified for microwave sensing. That was our first job, and it was a very interesting new field of research between the material engineering and microwave engineering groups. We have developed this new chipless RFID sensor, and we incorporated multiple parameters in a single node. That is a unique achievement. We have also designated ID data for particular frequency bands and sensing data for a particular frequency band, so they can seamlessly but independently operate. So that is another innovation that we have brought in this design. This fully printable chipless RFID sensor is printed on a flexible substrate for robust application. So that means we can print directly to the packaging material, and that is the big achievement for ubiquitous sensing and tracking application. And that way you can materialize the vision of IoT, Internet of Things, and the smart cities. Finally, our few recent books. These three books. First book covered the advanced chipless RFID at 60 GHz using the imaging technique, that is actually electromagnetic barcode. And also we have developed maximum likelihood detection technique for enhancing the data capacity. Second one is the book is covers the signal processing in general for chipless RFID tag reading. And the third book that published before by Arctic House that covers many aspects of chipless RFID system and the reader architecture. Thank you for your attention.